is Daniele Pinton, and he is a PhD student in the Department of Civil and Coastal Engineering at the University of Florida. Since spring of 2019, Daniele has been a part of Dr. Alberto Canestrelli's lab, which mainly focuses on improving numerical hydrodynamic and ecomorph dynamic models in coastal, estuarine, and riverine environments. His research primarily focuses on implementing a numerical model to forecast the distribution of pollutants in the GTM estuary. To improve the efficiency of his high-resolution numerical model, he focused on the use of new technologies, such as high-resolution UAV-based LiDAR, to describe the morphological and ecological features of coastal wetlands. And today, Daniela will be sharing about spatially explicit oyster biofiltration services in a subtropical estuary. I will go ahead and pass the controls over to you.
Okay. I think I don't have it. Okay. Thanks a lot.
Thank you.
So thanks a lot for the presentation. So today I'm trying to explain you what we did in the Guanajuato Matanzas estuary. And basically we try to describe the biofiltration services of oysters in this estuary. First of all, I wanted to thank all my co-authors, my colleagues, and especially Matthew Gray, Dr. Gray, who is leading this project. So to achieve our objectives, our results, first of all, we have different objectives. We want to quantify the resident time in the GTM NER at different spatial scales, so the local, the watershed, and the estuary scale. Then we want to quantify the filtration services of the oysters in the area and to determine which hydrodynamic and ecological variables could be used to predict the filtration services of the oysters inside the estuary. And the methods are based on 3 steps. So first of all, we want to determine the distribution of the ecological properties of the oysters inside the estuary, simply interpolating using an interpolation method. And then we want to determine the filtration services of the oyster using a MATLAB algorithm, and which is using the results obtained from a couple hydrodynamic plus particle tracking model. And then we want to determine a formulation, as I said, to determine the filtration services using a genetic algorithm. So the study site, obviously, is the Guanajuato Matanzas National Estuary Research Reserve. I want to stress you a lot about this. I simply want to say you that our model goes from this line to this one. So these are the northern and southern boundaries of our numerical model. I will explain later. So why we choose this area? Obviously, because as many of the coastal wetlands is a very good habitat for many species, which are good not only for food, but also because they provide a lot of valuable effects to the water. They clean it particularly. And the species we choose is this one. So it's the eastern oyster, the Chrysostera virginica, which has many good properties. First of all, it improves water quality in the area. It facilitates denitrification. And it do that by removing microparticulate material from the water. We know that these oysters live in these reefs, they populate them, and there are a lot of them inside the GTM NER. Basically, there are 4,300 reefs populated with alive oysters inside the area. And what GTM people did was to survey them, almost 250 of them. They surveyed a lot of data. We took only some of them, the oyster density and the shell length. And what we did was to take the data from the monitor reefs, which are described by the stars in the image, and using an inverse distance weighted interpolation, we simply define these values inside all the green dots inside the area. So the first part of the model is the hydrodynamic model. It's a delta 3D flow model. The cell dimension inside the domain is pretty different everywhere because we want to get different results in the ocean, and we want to have better results, obviously, inside the estuary. The simulation period goes from the 9th of May to the 10th of June 2018, and the time step is 1 minute. And the bathymetry comes from different sources, and these are the sources for the ocean and for the estuary. So here in this figure, you can see all the stations where we took the hydrodynamic, the water quality, and the weather data we used as boundary condition for our domain. And the stations are the dots, basically. And the squares are the place, and also these lines here are the places where we put our boundary conditions. So the second part of the model is the particle tracking model, and it's again a Delta3D model. Is the part model of Delta3D, and what we did basically was to take the area to discretize it using a regular grid that has this dimension of the cells. We determine which of these cells are wetted at least one time during the simulation period, and these are all the cells. These are divided in intertidal and subtidal areas. And what we did was to take these cells and to release particles at the center of these cells. We have 6 injections in our study period, one every 2 hours for the first 12 hours, so to cover one tidal cycle. And the time step of the simulation is again 1 minute. So to start, we have some result about the resident time, the local resident time, local scale resident time, which is calculated above the grids I explained before, I described before. And here you can see we have very different values inside the estuary. It is not uniformly distributed. Obviously, we have higher values of the resident time of all the marshes that goes from 7 to 214 minutes from the edges to the platform of the marsh. And we have higher values going from 3 to 5 days close to the mainland because the particles are stuck in these areas. And so this value grows a lot. And for the channels, we have lower values, obviously, that goes from 1 minute here at the inlets and reaches 7 minutes, about 7 minutes along the channels, obviously, because the velocity are lower. And the lower values of this resident time are placed here at the southern part of the estuary. So about the watershed and the estuary scale resident time, these are the results in days. So you can see the values are again not uniformly distributed, are pretty different in each of these watersheds. We decided to use this watershed to discretize the domain. And it seems like it is changing a lot because the watershed has a different dimension, also because there are different distribution of the marshes inside them, and also for their shape, the shape of the watershed. How we calculate these values? Obviously, we use an one over E method. So these graphs describe how the particle number goes with the time. And here, when the particle number reaches the 36% of the initial values, we have the resident time. These are the values for the watersheds, and this is the value for the entire estuary. The principle is the same, and the value we got is almost 14 days, so 2 weeks. That is pretty close to some results obtained from other authors before us. So to calculate the filtration services, we use many formulas. I put only the most important here for you in our MATLAB algorithm. So basically, we calculate the filtration rate at the oyster scale, which is the volume seawater filtered per unit time by each animal. It is obtained using these formulations. We couple these two formulations. We got these. This is a no, I'm sorry about that. And this is a DTW. It is the dry tissue weight that is calculated using this formulation. So these data are data measured inside the GTM, the shell length, and the dry tissue weight. And we found this formulation to describe the dry tissue weight using the shell length for all the oysters inside our domain. And this is the temperature. So it goes with the weight of the oysters and the temperature of the water. Multiplying this value by the total number of oysters inside a reef, we have the filtration rate of the reef. And then we have the filtration services, which is that is the percentage of pollutant mass filtered in the estuary within a single estuary resident time. The value is calculated in percentage, and it is proportional to the sum of the x. What is the x? The x is simply the changes in the mass of the particles moving inside our domain when they pass through the reefs. And I will explain later how we calculate these and how this works. But basically, this value depends on the volume of the water above a reef, on the filtration rate of the reef, and on the time spent by the particle over each reef. So basically what we did was this. So we took each particle, we released here in the middle of these cells, and we choose an initial particle mass of 100, and each particle has the same mass, and it didn't change in time. So we didn't add any kind of mass. It is only decreasing, and it is decreasing when the particles goes over the reef. Proportionally, it decreases proportionally to the filtration rate, and proportionate to the properties of the oysters over each reef. So these are some results we got from our algorithm. These are the filtration services at the reef scale and at the watershed scale. These values are the colored dots here in this figure, and these values are the values inside the box here, the white box. This goes from 0 to 0.9. Again, sorry about that. And basically, we see that these values are practically how much the percentage of pollutant mass, of the initial pollutant mass inside all the estuary that is cleared, it is filtered by the oysters in each watershed. And summing all of them, we saw that we have something like 59% of the mass that is completely filtered by the oysters. We saw another thing, that the value depends a lot, again, on the dimension of the watershed, of each watershed. So what we did was to divide this value by the area of the intertidal area, sorry, of each watershed, and we got these values. And as you can see here, everything changes, because here, these are the two watersheds that are providing the best values for the filtration rate at the watershed scale per unit of watershed area. And so these two watersheds are more efficient than this one, and then this one, and then this one, but they are not providing the same value just because they are smaller. And this is a very important thing to notice. Another thing we did was the same for the reefs. So we simply took the filtration services at the reef scale, we divided by the area of the reefs, and we got these values here. And these are the mean values for each watershed. Again, we observed that the distribution is not uniform, and there are some differences in some of them. And the most important one is the difference from between the 1 and the 8. So these two watersheds. This one is extremely high, this one is extremely low, but why? It depends a lot, we think, on the distribution of the reefs inside each single watershed. These values are the percentage of the area of the watershed that is covered by the reefs. And so here you can see, if there are a lot of reefs inside the watershed, the efficiency of each reef is not very high, because they are competing a lot because they are trying, anyone is trying to get the mass from the particles flowing and moving inside the estuary. So they are competing a lot. And basically, this is a very good estimator to describe what is going on inside the estuary and the watersheds.
3 minutes.
Thanks a lot. And this is described by this formula. As you can see here, the filtration services at the watershed scale depends linearly on the area of the watershed, on the average value of the filtration services per each reef, and on the distribution of the reefs inside the watersheds. Then what we did was to predict, we tried to find a formulation describing the filtration services at the reef, on the reef area, per reef area, using a genetic algorithm. And we choose these predictors. But why we choose them? We choose them because are part of the formulation we are using to describe the filtration services. So here we have the concentration, that is the X divided by V in a formula I explained some slide before. This is the filtration rate, of the oysters. This is the area of the reef, and this is the time spent, as I said before. If we take this area, we divide everything by the area of the reef, we get the filtration services at the reef area per unit of reef area. And we saw that it is proportional to the number of the particles flowing above each reef on their resident time, and they depends on these, some on the number of times and some on the number of particles flowing over the reef, on the average concentration of the cell of the particles entering the reefs, and on the filtration rate of the oysters over the reefs. We took all of them, we put them in the genetic algorithm, and we saw that individually they can give a lot of information to us. So the formulation we got are not pretty good. But when we put all of them inside the genetic algorithm, we got this formulation, this formulation. And it is pretty good. All the statistical predictors are pretty good. And the most important thing is that there is not the resident time. So basically, the genetic algorithm is saying us that all the values are important, but not the resident time. And it is pretty important because in the past, many authors, many scientists were focused on determining how the resident time was the most important predictor in describing how much an estuary can be filtered. And here, our results said that the resident time is not important. And so this is our take-home message, the most important message we got from our study. To conclude, I simply want to say that about resident times, they are not uniformly distributed in the GTM at each scale, so at the local scale and at the watershed scale. And for the filtration services, we got very good results because the oyster reef are filtering the 59% of the mass inside the estuary. And the most important thing is that the 40% of the mass that is not filtered is only partially inside the estuary. So only the 20% is inside the estuary. The other 20% is outside. And so basically we are, after 2 weeks, the GTM, the estuary is filtered of, we have a filtration of 80%. So we filter a lot of the pollutants inside our estuary. Then the spatial distribution of the filtration services at the reef and the watershed scale is not uniform in the estuary. At the watershed scale, the filtration services depend on the distribution of the reef, as I said before, and on the proportion of the watershed wetted area, that is the intertidal area they occupy. And then that the filtration services per unit of area depends on the number of particles entering the reef, on their concentration, and on their properties of the reefs, but they don't depend on the resident time. And with that, I want to thank everyone, and I'm glad to take any question.
Thank you so much, Daniele. Do we have any questions from the chat box? All right, and are there any raised hand questions? Several kudos and great work.
Thanks.
I know I really like the illustration or the animation that you had showing the particle movement. That was really a great way to visualize that data. Thank you.
You're welcome. Thanks a lot.
All right. Well, thank you so much. And feel free to type any questions into the chat box as they come to you. And thank you so much for sharing that project with us today. We're looking forward to seeing how it moves forward.